Good morning, everyone. Thank you for coming. It's an honor to be here with you today. Have you used React Server Components? Have you heard of Waku? Ever since React Server Components was announced, I've been curious about its capabilities and how client state interacts with it. The title of my talk is Developing Waku and Exploring Client States with React Server Components. Let me introduce myself. I'm DAISHI KATO. I develop open source libraries for React. I love coding, and I believe open source is a great way to collaborate and share ideas. Some libraries I developed are Zastan, Jotai, and Varshio. They are all state management libraries for React. If you use any of those libraries, thank you. You may wonder why I created 3 of them. Long story short, they solve different problems. So I created different solutions. One thing they have in common is that they are small and simple. I like simplicity. I don't like combining different ideas into a big library. Recently, my work has been focused on React Server Components. I'm developing a new framework, Waku. Today's talk about Waku. This talk consists of 3 parts. In the first part, I will introduce Waku. I will explain a hello-world example to show some features of Waku. In the second part, I'll talk about what's unique about Waku. I will share my thoughts and my vision for it. In the third part, I will introduce the Waku Jotai library. It's a Jotai integration library for Waku. I'll discuss some technical details. OK, let's get started. So what is Waku? Waku is a React framework. It's built for React Server Components from day one. Like my libraries, I want it to be simple and minimal. Frameworks are usually big and provide many features. My preference is to provide only the essential features. If we want more features, we should be able to create them our own. That's the philosophy of my libraries. I want to apply the same philosophy to Waku. I'm not sure if you feel it, but let me walk you through our Waku starter project. Before jumping into the starter project, here is Waku's website. When you first visit the site, you'll notice the page is very long. And it's intentional. We wanted to make sure that it covers all the basic information you need to get started. It even includes some explanation about React Server Components for developers who are not yet familiar with it. Next, I will explain how to create a new project, how to run it, how to build a static site. Then I will show you how to make a dynamic site. Let's see how to create a Waku app. To create a new Waku app, you can use the npm create command, or you can use your favorite package manager. If you run it, it will create a starter project for you. After the command finishes, let's go into the project directory, then start a dev server. You should see the starter page in the browser. That's it. Your app is running, and you can start developing. The starter project has 2 pages, which are server components, and it has 1 client component. Even though it's a tiny project, it shows some key features of Waku. Now, let's look at the source code structure. Here is the source code structure of our starter project. This list shows the files in our source directory. The important directory is source pages. It is for file-based routing. We have to follow some conventions in this directory. For example, the file name becomes the URL path of the page. On the other hand, the source components directory is for reusable components that are not tied to pages. In this case, the directory contains both client components and server components, but it's up to you how to organize them. Let's look closely at the code of a page. Source pages index.tsx is the file for the top page. This file must export a React component as the default export. Page components are server components by default. As you can see, it's an async component, and it can await a get data function. It is possible because it's a server component. Most notably, it exports a getConfig function. This is a WACC-specific function. It provides configuration for the page, such as render mode. Other pages like the About page follow the same conventions. Let's edit the headline of the page. On the left, you have an editor. On the right, you have the browser. Open source pages index.tsx in the editor. You can use your favorite editor. Find the headline WACC, replace it WACC2 and save the file. You'll see the change in the browser. No refresh is required. The browser updates automatically. Do you remember this is a server component? It means WACC enables hot reloading for server components. It's time to build our app. If everything is static, we can build a static site. Currently, our app is completely static. So let's run the build command. Would you like to see the build output? The build output for a static site is in the dist public directory. You'll see some HTML files like index.html and about index.html. There are also some assets like CSS and JS files. Most notably, there are files in the RSC directory. They are the serialized React server components. If you are curious, you can open them. They are just text files. It looks like this. Anyway, to deploy the static site, upload this directly to any static hosting service. Or we can try it with the serve package from NPM. It works mostly like a static hosting service. Let's try that. Let's run the serve command and open the browser. And it works. It runs without any server. So far, we've seen that WACC can build static sites. But it's not limited to static sites. We can also build dynamic sites using the server. To demonstrate our dynamic site, let's make the index page dynamic. To make a page dynamic, we need to export the getConfig function from the page file. This function returns a config object. The render property in the config object can be either static or dynamic. If we set it to dynamic, the page will be rendered on each request. To see this working as expected, let's add a timestamp to the page. Now, we build the app again and start the server. The browser shows a page with the current server time. Let's jump to the About page and go back. The time has changed. This means the page is rendered on each request. In many cases, we want to deploy our dynamic site. A dynamic site requires a server. Our first option is a Node.js server. By default, WACC builds for Node.js, and you can run it on any Node.js server. Alternatively, we can deploy our app to cloud services. WACC supports Vercel, Netlify, and Cloudflare workers. We are working on supporting more cloud services. All right, that's it for building and deploying our Waku app. We learned the basic usage with the starter project. Unfortunately, not all features are included in the starter project. There are more features in Waku. I can't cover all of them in this talk, but before finishing the introduction of Waku, let me briefly introduce 3 routing features. The first feature is segment routes. We can handle multiple routes with one file. We use bracket notation to define a segment. The second feature is group routes. We can use a shared layout for a set of pages, and we use parentheses to define a group. The third feature is slices. We can define cacheable components that can be used across pages. It's a brand new feature of Waku. I think we'll find more use cases as we go. All right, that was the introduction to Waku. In the second part of my talk, I will explain the philosophy of Waku and why I created it. I introduced myself as an author of state management libraries. And because I work on those libraries, I get a lot of questions from the community. One of the most questions I received was this: how can we use our favorite client state management solutions with React Server components? It's a great question, and for a long time, I didn't have a good answer. The easy answer was, you can't, because client state doesn't work on the server. But this answer isn't very helpful. I thought the real question behind it was, what's the developer experience? How should it be? I believed there must be a way, but at that time, my knowledge was limited. Furthermore, there was very little documentation about how React Server components worked under the hood. Then I realized that the only way for me to explore this space was to build something myself. It started as a personal research project. It was a tool that I needed to begin my exploration. I started developing Waku in March 2023. This chart shows the GitHub start history, and you can also see some major events on the right. It wasn't a framework at first. It was more like a playground. I didn't know what was required to be a framework. Things changed when I received feedback from people. I started to understand what a framework should be. For example, we needed a router to call it a framework. Soon afterward, I noticed that many people expected SSR in frameworks. My original opinion was that SSR is different from React Server components, and that SSR is optional. But now SSR is integrated into Waku by default, and you can still opt out of it. Eventually, people started asking if they could use Waku for production. At first, I was a bit hesitant. I wasn't sure how ready it was. My mind changed when collaborators joined the project. We formed a team and started aiming for a production-ready framework. It took some time to get here, but now Waku is reaching its V1 alpha version. We encourage advanced users to try it for their projects. Based on their feedback, we should be able to release the V1 stable version. Now, let me explain what I think makes Waku unique. We call Waku Minimal React Framework. What does minimal mean? Actually, minimal here has 2 aspects. The first aspect is the public API surface. We keep the public API small and easy to learn. This helps new users get started quickly. I hope I was able to explain that in the first part of my talk. The second aspect is less obvious, but important to me. This is related to my original motivation. I'll focus on the second aspect for the rest of this talk. My motivation was to build a library that could integrate with React Server components. In other words, I wanted to extend the React Server components framework. That brought me to the idea of a minimal API. It may not be widely known, but the basic capability of React Server components is primitive. At the core, it is to serialize React components on one end and deserialize them on the other end. What I would like to achieve with Waku is to provide a primitive capability of React Server components. We call it the minimal API. The minimal API exposes low-level functions for serialization and deserialization, and also follows the best practices of React Server components. You can think of it as exposing the internal functions of the framework. The minimal API is designed for library authors, including myself. You can build new functionality based on the React Server components capability. Our goal is to build an ecosystem around Waku. We want library authors to build libraries on Waku. They can use the minimal API to build libraries that integrate with the framework and become part of the ecosystem. As an interesting example, the official router of Waku is built on top of the minimal API. This means that the router is a library, not part of the core. When we explain to the framework users, we don't clearly distinguish between the core and the router, but technically it's a separate library. This is interesting because that means we can build a different router if we want. In that sense, Waku is a router-agnostic framework. I hope this architecture with the minimal API helps grow an ecosystem. I believe this vision of a minimal, extensible core is what makes Waku unique. By now, I hope you know what Waku is, why I created it, and the philosophy behind it. Let's move on to the third part of my talk. Let's back up a little bit and talk about Jotai. Jotai is one of the state management libraries I developed. The Jotai atom model is interesting. The atom definition doesn't hold the atom value. Instead, an isolated store holds the values of atoms. This code snippet should show the idea of stores. We define a count atom and double count atom with the atom function. Then we create a store with the createStore function. We can set the value of an atom in the store using the set method. Then we can get the atom values from the store using the get method. As you can see, a Jotai atom acts like a key, and Jotai store is like a map. Internally, it uses a weak map, so atom values are garbage collectible. We've seen how Jotai store works. Typically, we use a single store in application. But we can have multiple stores, and there are some use cases for this. With multiple stores, we can reuse the same atom definition across stores. This means we can have different values for the same atom. Jotai uses this capability with React context. We can scope a Jotai store to a specific part of the component tree. To me, this implies that it's possible to have a Jotai store on the server. It may sound confusing at first, but my point is that if we have a jotai store on the server, we can reuse the same atom definition on the server. As I said, values can be different across multiple stores. This brings up a new question. Can we sync the values between the client store and the server store? If we could do this, it would open up new possibilities. That is where the idea of server store comes in. What does it look like to use jotai atoms on the server? Before diving into the idea of server store, let's understand the server. The key thing to understand is that the server doesn't have state like the client does. We should assume that the server is stateless. When a request comes in, the server processes it and sends a response. The server forgets everything after the response is sent. One idea is to create a new jotai store for each request. While this works for using atoms on the server, it's a limited approach. It doesn't solve the real problem. It doesn't provide a nice developer experience. What we want to achieve is using jotai atoms on the server that are synced with client atoms. So you can read the client atom on the server. But is it possible? Again, our technical question is how can we sync the client store and the server store? This is a challenging problem. Some of you may know that jotai atoms are distinguished by reference. They don't depend on a string key. But we can't serialize a reference in general. To solve our problem, we need to serialize the atom reference. If we had a string key for an atom, it would be easy. But having such a string key goes against jotai's design. Well, if we remember how React server components work, this isn't a new problem. We import client components with the useClient directive. The framework then creates a serializable client reference. Can we use the same mechanism? The answer is yes. The useClient directive is not just for client components. It works for any client value, including jotai atoms. Here's how it works. If we export atoms with the useClient directive, we can import them on the server. Then we get a serializable client reference for the atom. We map this reference back to the actual atom on the client. This mapping is the key. This lets us sync the atom value between the server and the client. There are still challenges, but the point today is that with serializable client references, we can sync the client store and the server store. This brings us to server-only atoms. Once we have a synchronized store between the client and server, we can do something interesting. On the server, we can define a server-only atom that interacts with server-only resources, such as a database. The server-only atom can read the client atom, and it feels like the boundary between the client and server disappears. Wouldn't that be great? Let's look at the pseudocode snippet. This is server code. In this case, we have a count atom, which holds a number. Let's assume this atom is somehow synchronized with the client. Then we define a scaled count atom, which is a derived atom. This atom reads the count atom and multiplies it by a factor. As you can see, the factor comes from a database that only exists on the server. It's possible because the scaled count atom runs only on the server. We call it the server-only atom. This is still pseudocode, but I hope you get the idea. Do you notice that the server-only atom is like a server component? It runs only on the server, and only the result is sent to the client. We don't send server code to the client. Just like a server component, a server-only atom can contain server logic. I really like this idea of server-only atoms, but to make it work, we need to solve the updating problem. When the count atom on the client changes, how do we update the scaled count atom on the server? This must trigger a re-render on the server and then send the rendered result back to the client. Is it even possible to implement this? It wasn't easy, but I made it. I made an experimental library called Waku Jotai. To implement a library to solve these problems, we need a framework that gives us full control. This is where Waku comes in. Waku provides the minimal API, which is a set of low-level APIs of the framework. With the minimal API, we can build a library that solves the problem. And the Waku Jotai library was born. With Waku Jotai, we can define server-only atoms, and our server store is synchronized with the client store. It works seamlessly behind the scenes. Library users don't have to worry about how it works. Now, the fun fact is, the truth is actually the opposite of what I just explained. First, I wanted to create a Jotai integration library, but no such framework existed. So I created Waku, and I created the low-level APIs, so I could build the Waku Jotai library. But believe me, the low-level APIs are designed to be general enough for other use cases. Let's look at the source code snippet to see how to use Waku Jotai library. This is a client code from the working demo. You'll see use client directive at the top. We define an atom and a component here. The main thing to note is the allow server function. It's exported from Waku client. It's still unstable, but what it does is to expose atom's initial value to the server. Other than that, it's regular Jotai client code. The counter component and use atom hook should look familiar if you have some experience with Jotai. Now, the server code includes something different. This is a server code. In the first few lines, we see some import statements. One important import is get store from Waku Jotai router. Then we define a server-only atom, double count atom. It reads the count atom and multiplies it by 2. Count atom is a client atom, so we expect its value is synchronized with the client. It waits 1 second to simulate some server delay. But as this is just a demo, it doesn't include any real server logic. But I hope you get the idea. This file exports a server component page. In the server component, we call the getStore function to get the Jotai store. Using the store, we can read the value of double count atom. Do you remember the store get method I explained earlier? We don't use hooks like useAtom because this is in the server environment. There are some tricks behind the scenes, but I hope you see the overall picture. That is, we can define server-only atom just like client atoms. The framework takes care of the synchronization and updates. Does it really work? Let's see our demo. This is a running demo based on the code snippet I just showed. It's a tiny application. We can see the browser network tab on the right. We have a button to increment the count. When we click the button, the count increases. The network tab shows that a request is sent to the server. The server then re-renders the server component. When the browser receives the response, it updates the UI. Again, our demo doesn't include any server-specific logic, but you can see it communicates with the server for each update. We know that the server-only atom runs only on the server, and it can interact with server resources such as database. This will bring a new power to the Jotai atom model. Well, this is just the beginning of Waku Jotai library, and it's just one library in the Waku ecosystem. Do you see the potential and the future of Waku? As we saw, the Waku Jotai library enables a new pattern of server-only atoms with React Server components. Again, the important point is that this library is not part of the framework. It's just a separate library. This means Waku provides sufficient APIs to implement such functionality. This is key to our vision. Waku exposes APIs so library authors can build an ecosystem. We should be able to develop libraries for other state management tools like Zastan or Varusio. We could even have different routing libraries. That's the future I would like to see for Waku. It has been a long journey from a personal experiment to a community project. If you are interested, please try Waku and share your feedback. I'm excited to see what you build with it. Thank you for your attention.